So let's keep going with chapter 1. Just to remind ourselves, this should be mostly review, but if it isn't, pay attention. All the concepts here are kind of important. Okay, so the section 1.2 has to do with graphing equations and finding intercepts. Also some stuff about symmetry. So here are our main objectives. Can we graph equations by plotting some points that satisfy them? Can we find intercepts from a graph? And the word intercept from a graph or an equation will be defined in a bit. Can we test to see if an equation has some symmetry? And can we graph some specific equations that we're going to refer to a lot? So, well, what is an equation? We have two variables. We'll usually be using x and y. We might sometimes use t instead of x. The names aren't so important. And then it's an equation, so we should have an equals sign in them. The equal sign has a left and a right side. These are the sides of the equation. If there's a choice of x and y that make both sides actually equal, then that choice of x comma y is said to satisfy the equation. And if that xy satisfies the equation, well, then you've got a coordinate. Okay? And if you draw all of the coordinates that satisfy an equation, that's what's called the graph of an equation. It's all of the points where the equation is true. So let's take an example. Here is an equation. 3x minus y equals 9. Sometimes it's true and sometimes it isn't. Let's check. So for the point 3, 2, we identify that x is 3 and y is 2. So I'm going to put it into this equation. 3x is 3 times 3, minus y is minus 2. That's 9 minus 2, and I get out 7. So this left side, 3x minus y, is 7, and the right side was 9. Is 7 equal to 9? No, it isn't. So the point 3, 2 does not belong to the graph of this equation. Remember, the graph is all of the points where it's true. Since it's not true at 3, 2, 3, 2 is not on the graph. Well, what about the point 2, 3? So now I take x equals 2 and y equals 3, and I stick them into 3x minus y. 3 times 2 minus negative 3. 6 plus 3, which is 9, which really is the same as the right-hand side. So 2, negative 3 does satisfy the equation, and therefore does belong to the graph. So can we find all of the points that satisfy this? Okay. So generally, there's going to be a whole lot of points that satisfy an equation, infinitely many of them, in fact, and therefore, you really can't expect to find them all. But we're going to check a couple of things, okay? So we had, here's our new, it's a new equation, is equal to negative 3x plus 3. If I make a choice of x, for example, I'll start at the middle, if x equals 0, well, if x equals 0, then y had better equal negative 3 times 0 plus 3. Negative 3x, which was 0, plus 3. What's negative 3 times 0 plus 3? Negative 3 times 0 is 0, plus 3 is just 3. So if I had x equals 0, there's only one possible choice of y that's going to make this work out, and that's y equals 3. So the point 0, 3 is on the graph, and in fact, it's the only point on the graph where x is 0. Okay, I make other choices, like what if x is 1? Well, then y had better be 0. So not only is 1, 0 on the graph, it's the only point where x is 1. Because if I started by saying, hey, what if x equals 1, the only possible value of y was 0. Similarly, if x is negative 2, y has to be 9. If x is negative 1, y has to be 6, and so forth. Now, if we plot these points, negative 2, 6, negative 1, sorry, negative 2, 9, negative 1, 6, 0, 3, 1, 0, and 2, negative 3, there they are. Observe that it kind of looks like this straight line connects all of those points. And that happens to be true. Let's try to graph the equation y equals 1/2 x squared. So again, if I make a particular choice of x, then y has to equal 1/x squared. 1/2 times negative 2 squared is 2. So if x is negative 2, y has to be 2. If x is negative 1, you do this computation here, y has to be 1/2. If x is 0, y has to be 0. If x is 1, y has to be 1/2. If x is 2, y has to be 2, and so forth. If I plot these points, here's -2, 2, -1, 1/2, 0, 0, 1, 1/2, and 2, 2. Notice they're not in a straight line. I can't draw a straight line that connects all of these points. It's some sort of curvy thing that turns around. It's going down, and then it seems to come back up. This is called a parabola, this particular curve. Not every curve is called a parabola. This one is called a parabola. We'll get more into that. Okay. What's an intercept? Remember, we started off with our y-axis and our x-axis. Where a curve crosses through an axis is called an intercept, either an x or a y intercept, respectively. Okay. So where it touches the x-axis is called an x-intercept, and where it touches the y-axis is called a y-intercept. So here is the y-axis. When it goes through the y-axis, that's called a y-intercept. Where it goes through the x-axis is called an x-intercept, and there might be more than one. Okay, so find the intercepts of this graph. What are its x-intercepts? What are its y-intercepts? Pardon me. Well, where does it intercept the x-axis? Right here and right here. Does it intercept the y-axis? Right there. So the x-intercepts are at -4 and 3, and the y-intercept is at -3. Those are the x values and the y values of the x-intercepts and y-intercepts, respectively. So suppose you're given the equation. Okay, you're not looking at the picture, you're just given an equation. Can you find the intercepts? Yes, so here are our axes. Notice the x-axis is a horizontal line. Every point on that line is at the same height. What is the height of the x-axis? It is of height 0. So it's actually given by y, or the vertical component, or the height, is always 0. The y-axis goes up and down, but does not move left and right. Everything on the y-axis has the same horizontal component. And what is it? X is 0. So if I want to find where do I cross the x-axis, the x-axis says make sure that y is 0. So if I want to find x-intercepts, let y be 0. If I want to find y-intercepts, let x be 0. Okay, so let's do an example. Y equals x squared minus 9. Find the x and y-intercepts, and then plot some points on it. So to find the x-intercepts, I let y be 0, and we say x squared minus 9 is 0, because I just took the equation. Here it is, y is x squared minus 9, and I said finding x-intercepts, make sure y is 0. X squared minus 9 factors as x minus 3, x plus 3. How can the product of two numbers be 0? Either the first number, x minus 3 is 0, or the second number, x plus 3 is 0. Most students would actually do this slightly differently. They'd say x squared minus 9 is equal to 0. Therefore, if I add 9 to both sides, that cancels here, and I get x squared is equal to 9. And then a lot of people would make the following mistake. They'd say, so x is root 9, which is 3. But if x squared is 9, if x is positive, it's definitely 3. Don't forget, when you take a square root, you probably want a plus or minus square root. So x is actually plus or minus 3. X is either 3 or x is minus 3. Two separate ways to do the problem, both perfectly legitimate, as long as you remember to do the plus or minus square root. Okay, so there are two x-intercepts, 3 and -3. What about a y-intercept? So here was my original equation. I'm going to let x be 0. So y is equal to 0 squared minus 9, which just gives me y is minus 9, and there's the only y-intercept. And now can we plot some points? So the equation is y equals x squared minus 9. If I just start plugging in some values for x, we end up with these values for y. And so we can plot those points. And again, it goes down and then seems to go up. This happens to be another parabola, which means it's going to graph kind of like that. Yeah. Okay, some graphs are symmetric. So a graph is symmetric with respect to the x-axis means if this point is on the graph, x comma y, then the same point reflected down, x comma minus y, has to be on the graph. So if you can ever find an x comma y, you have to find the same thing with minus y. Notice this doesn't say y has to go from positive to negative. It's perfectly plausible for this y here to be negative, and then this one becomes positive. It's a really, really easy mistake, and students do it all the time, to think, oh, this variable has a minus sign in front of it, so it's the negative one, or this variable doesn't have a minus sign in front of it, so it must be positive. But there's no reason to suspect this. Y could be positive or negative, which means negative y could be negative or positive, as long as it's just the opposite. Okay. So, for example, if the point 5, 3 is on the graph and it's symmetric, then 5 minus 3 must also be on the graph. Symmetry with respect to the y-axis is very similar. It's just if xy is on the graph, negative xy must also be. If xy is on the graph, then the same point with the x-coordinate reflected must also be on the graph. So if 5, 3 is on the graph, then so is negative 5, 3. And this is symmetric with respect to the y-axis, or sometimes called symmetric across the y-axis. If you have the property that if xy is on your graph, then so is the point where both of them are flipped, that's called symmetric with respect to the origin. So if 5, 3 is on the graph, then if I just go straight through the origin and look at the point negative 5, negative 3, then that's on the graph. This is why it's called symmetric across the origin, because any point here will be reflected straight across the origin to its sort of mirror image that way. So you can test for all of these symmetries by doing something pretty simple. Symmetric across the x-axis means if xy is on the graph, then so is x minus y. So how do I test that? Replace all of your y's with negative y's and see if you get exactly the same thing. Similarly, to test for symmetry across the y-axis would be if xy is on the graph, then negative xy is. So replace all your x's with minus x's and see if everything still works out to be exactly the same. And if replacing them both means nothing really changes, then you are symmetric across the origin. So test 9x squared plus 16y squared equals 25 for symmetry. So what happens if I replace y with minus y? The only time y appears is here, so I replace it with negative y. But notice negative y squared is the same thing as just y squared, so nothing actually changed. Therefore, it is symmetric across the x-axis. Replacing y with negative y did not change anything. Is it symmetric with respect to the y-axis? So I replace my x with a minus x, but again, negative x squared is the same thing as x squared, so this equation, we started with 9x squared plus 16y squared equals 25. When we replaced y with negative y, nothing changed. It was symmetric across the x-axis. Now we're doing, is it symmetric across the y-axis? Replace x with minus x, nothing changes. So yes, it is symmetric across the y-axis. Can I do both? Absolutely. Replacing x with negative x and replacing y with negative y both didn't actually change anything. So I can make both switches. It is symmetric across the origin as well. How about 6x squared over x squared plus 2 equals y? If I replace y with minus y, I don't get the same thing because this entire expression doesn't change. It doesn't have any y's in it, but the left-hand side did. I got a genuinely different thing. So it is not symmetric across the x-axis. Replacing y with negative y actually changed something. It made the left-hand side have a minus sign and didn't do anything to the right, so it's not the same thing anymore. However, if I replace all of my x's with y's, with minus x's, sorry, if I replace my x's with minus x's to test symmetry across the y-axis, Negative x squared is the same thing as x squared. Again, in the denominator, negative x squared is the same as x squared, so nothing actually changed. It is symmetric with respect to the y-axis. Is it symmetric with respect to the origin? No. If I replace my x's and my y's with their minuses, the right-hand side is the same as it was before, but the left-hand side isn't. So it's not the same thing anymore. So it is not symmetric with respect to the origin. So let's sort of summarize a bunch of stuff together. Can we graph the equation y equals x cubed by finding intercepts for symmetry? So how do I find intercepts? To find the y-intercepts, let x be 0. To find the x-intercepts, let y be 0. But in this case, since y is x cubed, if I let x be 0, I just get y is 0. So my only y-intercept is when I let x be 0. The only y-intercept is y equals 0. On the other hand, if I let y be 0, I get 0 equals x cubed. The only way x cubed can be 0 is if x equals 0. So the only y-intercept, the only x-intercept by letting y equal 0, the only x-intercept is also x equals 0. So x equals 0, y equals 0, 0, 0, it's the only intercept. Now test for symmetry. If I replace y with negative y, I don't get the same thing. The left-hand side changed, the right-hand side didn't. So there is not symmetry with respect to the x-axis. What if I replace x with minus x? Well, just to check the arithmetic, okay, if I replace x with minus x, I get negative x times negative x times negative x. In other words, I do get an x cubed, but I get a minus 1 times a minus 1 times a minus 1. That's a minus x cubed. So we end up with y equals minus x cubed. That's not the same thing as the x cubed we started with. So replacing x with minus x did not result in the same thing. Therefore, it is not symmetric with respect to the y-axis. Is it symmetric with respect to the origin? Try switching both. Well, I replace y with minus y, and I replace x with minus x. And we've already done the work on the right-hand side. Negative x cubed is just negative x cubed. So now I have negative y equals negative x cubed. If I multiply both sides by minus 1, I can cancel that minus sign out and just get y equals x cubed, which is what we started with. Therefore, it is symmetric with respect to the origin. Okay. And now let's just plot some points. If x is 0, 0 cubed, y has to be 0. If x is 1, 1 cubed, y has to be 1, and so forth. So if x is 0, y is 0. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and so forth. So here's, if x is, If x is 0, then y is 0. If x is 1, then y is 1. If x is 2, then y is 8. And the point has been moved, but if x is 3, then y was 27. And we're symmetric with respect to the origin, which means 1, 1 is on the graph, which means negative 1 is also on the graph. 2, 8 is on the graph. That means negative 2, negative 8 is on the graph. 3, 27 is on the graph. Therefore, way, way, way down here, negative 3, negative 27 is also on the graph. Can we graph x equals y squared, find intercepts, check for symmetry? So again, if I let x be 0, I get y is 0. If I let y is 0, I get x is 0. The only intercept is still the origin, just like last time. Okay. There is some symmetry. If I replace y with negative y, nothing changes because it was being squared. If I replace x with negative x, however, then this left-hand side changes and this right-hand side doesn't. So it would not be symmetric across the y-axis. Replacing x with minus x, that was different. Not symmetric across the y-axis. But replacing y with minus y didn't cause a change. Therefore, it is symmetric across the x-axis. And if I switch both of them, then the left-hand side does change, but the right-hand side is actually the same as we started with. So that's different. It's not symmetric across the origin. Okay. If I start plotting some points, x is equal to y squared. It's easier to pick the value of y and then get the value of x. And so we can get some points, 0, 0, 1, 1, 4, 2, 9, 3. And then by symmetry, Okay, remember it was symmetric across the x-axis, so if 1, 1 is on the graph, then so is 1 minus 1. If 4, 2 is on the graph, then so is 4 minus 2, because I am symmetric this way. And these points join up in this sort of, it's still a parabola as a matter of fact, but instead of going up like the other ones we've seen, it goes out to the right. If we restricted y so that it had to be positive, so we're starting with x equals y squared, I can take the plus or minus square root here. If y has to be positive, then what I really want is just y equals root x, not negative root x. And if I graph that, it would just be this part here. Okay. Graph the equation y equals 1 over x. Find any intercepts, blah, blah, blah. Same as all the other ones. Notice if x equals 0, I get a 1 over 0, which does not exist. So there is no y-intercept. If x is 0, there is no choice of y that will make this work. Okay, so there's no y-intercept. But if I let y be 0, can I make 0 equal to 1 over x? Well, if I multiply both sides by x, on the right I get 1, and on the left I get 0 times x, which is 0. Is 0 equal to 1? No. So there are no x-intercepts either. There's no value of x, which can make 1 over x equal to 0. So this graph has no intercepts. Hey, it happens. Okay. So it doesn't touch the axes at all. Does it have any symmetry? If I replace y with minus y, I get something different because the left changed and the right didn't. If I replace x with minus x, the right changes and the left didn't, so it's not symmetric that way. But if I make both switches, if I replace y with minus y and I replace x with minus x, I can now multiply both sides by minus 1 and cancel those out and get right back where we started. So there is symmetry across the origin. Okay, we can plot some points. If x is 2, then y is 1 over x, that's a half. If x is 3, y is 1 over x, that's a third. But reciprocals work. If x is a half, then y is 1 over a half, which is 2. If x is a third, y is 1 over a third, which is 3. So we end up with these points here. Okay, but it is symmetric across the origin, so since this point is on the graph, if I reflect it across the origin, I get this point must be as well. Notice it's the same point, half 2, but it's negative a half, negative 2. That's what, remember what symmetry across the origin looked like. Okay, so there's a couple of graphs, some terms like symmetry and intercepts and all that. And again, hopefully some of this, if not most of it, we've done before. If not, that's okay. Acquaint yourself with the concepts. Maybe try a couple review problems from the section. And there we have it. That was section 1.2.